Another property of electromagnetic waves is polarization. The electric field vectors of an electromagnetic wave are in a plane perpendicular to the direction of the motion of the wave. That direction is called the plane of polarization. Light waves emitted by the sun have random polarizations. The light is called unpolarized. Most of light's interactions with matter is due to the electric field vector. Some long organic polymers allow electrons to freely move along their lengths. When the electric field of an electromagnetic wave is parallel to the polymer's length, it accelerates electrons in the polymer, thereby losing its energy and decreasing its magnitude in that direction. Electric field components that are perpendicular to this axis are unaffected, since the electrons in the polymer are not free to move in this direction. In this case, the electric field component of the wave loses no energy as it passes. Practical applications of this turn out to be things like sunglasses and light filters. Here's a practical picture of how polarization works. On the left is an unpolarized source of light. In the middle is a polarizer with the polymer chains running horizontally and perpendicular to the direction of the path of the light. And at the far end, we have an observation screen. As you note, as the light comes from the unpolarized source on the left, we can see various waves, all with different orientations around the direction of propagation. When all of these electromagnetic waves come in contact with the polarizer, only the waves perpendicular to these polymer chains, which are running in an up and down direction here, get through. And this leaves us with a polarized electromagnetic wave, which is, in this case, vertical, and that is what actually ends up hitting the screen or our eye or camera. Polarizing sunglasses contain these polarizing filters. They block horizontally polarized light, exactly the same way that we showed in the last slide. Since light that reflects off of water and other horizontal surfaces is mainly horizontally polarized, this light is blocked, and so it reduces the intensity of the light, the reflected light, the glare if you like, without losing any of the details. Let's consider the case of having some polarized light, which has a polarization angle that is different from the next polarizer. Because the intensity of a light beam is proportional to the square of the amplitude, the intensity of a plane polarized beam transmitted through a polarizer is going to be equal to I naught, that's the initial intensity, times cosine squared theta, where theta is the angle between the polarizer axis and the plane of polarization of the light. Note that the incoming light in this equation is already polarized. So, and this is important, when you're dealing with unpolarized light, you're going to pass it through one polarizing filter to produce some kind of polarizing light, and this reduces the intensity to 1/2 of the original. After that, you pass it through the next polarizer, angled at some angle theta relative to the first one, and that's when this equation I equals I naught times cosine squared theta is applied.